30,000 degrees Kelvin, 50,000 degrees Kelvin. Somewhere in that range, drifting silently at the very edge of our solar system, sits a region of space so hot that if you translated the number into Fahrenheit, you would be looking at something close to 90,000 degrees. That is hotter than the surface of most stars you can see in the night sky. That is hotter than the core of a bolt of lightning. And it was not detected in a lab, or in a simulation, or in a theoretical paper written by someone who never left Earth. It was measured directly by instruments built in the 1970s, riding on a spacecraft that is right now more than 15 billion miles away from where you are sitting. That spacecraft is called Voyager 1, and the data it beamed back across the void has forced scientists to rethink what actually happens at the boundary between our solar system and the rest of the galaxy. They started calling that boundary a wall of fire, and once you understand what is really happening there, you will realize that the truth is even stranger than the name suggests. To understand why this discovery matters so much, you have to go back to where this whole story begins, because Voyager 1 was never supposed to still be talking to us. It launched in the late summer of 1977, just weeks after its twin, Voyager 2, left Earth from Cape Canaveral. The mission planners at the time had a fairly modest goal by today's standards. They wanted to take advantage of a rare planetary alignment, one that happens only once every 175 years, where Jupiter, Saturn, Uranus, and Neptune line up in such a way that a spacecraft could use each planet's gravity to slingshot toward the next one, saving enormous amounts of fuel in the process. It was an elegant piece of orbital mechanics, but nobody involved in the project expected the hardware to survive much beyond the outer planets. The original mission was designed to last about 4 years. Instead, both Voyagers kept going. They flew past Jupiter and revealed volcanoes erupting on its moon, Io. They swept past Saturn and its rings in stunning detail. Voyager 2 continued on to become the only spacecraft in history to fly past Uranus and Neptune, giving humanity its only close-up look at those distant ice giants to this day. Voyager 1 took a different path, one that sent it away from the plane of the planets entirely, out into the darkness beyond, on a trajectory that would eventually make it the most distant human-made object in existence. For decades after those planetary flybys, Voyager 1 kept moving outward, farther than any spacecraft had gone before, sailing through what scientists call the outer solar system. This is a region far beyond Pluto, far beyond the orbits of any planet, where sunlight becomes so faint that at noon on Voyager 1 it would look like a bright star, rather than the blazing disk we see from Earth. Out here, the spacecraft is not really flying through empty space in the way people imagine. It is flying through a vast, invisible bubble created by our own sun, called the heliosphere. This bubble is made of something called the solar wind, a constant outward stream of charged particles, mostly protons and electrons, blasted off the surface of the sun and flung out in every direction at speeds of hundreds of miles per second. This solar wind carries the sun's magnetic field with it, and together they form a protective shield that surrounds the entire solar system, deflecting a large portion of the harmful cosmic radiation that fills the rest of the galaxy. Earth sits deep inside this bubble, comfortably shielded, and most people never think about the fact that our planet is essentially living inside the outer atmosphere of the sun, in a sense, long after that atmosphere has technically ended. But that bubble does not go on forever. As the solar wind travels outward, it gradually loses pressure, the way air rushing out of a punctured tire loses force the farther it spreads. Eventually, the outward push of the solar wind is no longer strong enough to overpower the material drifting between the stars, which scientists call the interstellar medium. This interstellar medium is not empty either. It is filled with gas, dust, and charged particles left over from other stars, supernova explosions, and the slow churn of galactic evolution over billions of years, where the solar wind and the interstellar medium meet and struggle against each other. Strange and violent physics begins to happen, and it happens in stages, not all at once. The first major boundary that Voyager 1 crossed on its way out was something called the termination shock. This is the point where the solar wind, having traveled for billions of miles, suddenly slows down abruptly, dropping from supersonic speeds to subsonic speeds almost instantly, the same way a boat's wake changes shape when it crosses from open water into shallower currents. Voyager 1 crossed this termination shock in December of 2004, at a distance of about 8.5 billion miles from the Sun. This confirmed decades of theoretical predictions, and it also revealed that the shock was much closer to the Sun than many models had suggested, which quietly hinted that the heliosphere might not behave exactly the way physicists had assumed. Beyond the termination shock lies a turbulent transition zone known as the heliosheath. Think of it as the compressed outer shell of the solar wind bubble, a churning region where the slowed and heated particles from the sun pile up against the pressure of interstellar space, like water piling up against a dam. This is a strange, chaotic environment, filled with twisted magnetic field lines, turbulent plasma, and particles bouncing back and forth in ways that are extremely difficult to model from Earth. Voyager 1 spent years crawling through this region, sending back data in painfully small increments given the enormous distance the signal had to travel, taking well over a full day, one way, just for a single radio transmission to reach mission control back on Earth. Then, in August of 2012, something happened that scientists had been waiting for since before some of them were even born. Voyager 1 finally crossed the heliopause, the true outer edge of the sun's bubble, the place where the pressure of the solar wind finally drops to essentially zero. And the spacecraft found itself immersed almost entirely in the plasma of interstellar space itself. This made Voyager 1 the first human-made object to ever leave the heliosphere and enter true interstellar space, a milestone that took years of careful data analysis to confirm because the signs were subtle, buried in tiny shifts in the density of charged particles measured by an instrument that itself had partially failed decades earlier. Scientists had to get creative, waiting for a solar eruption to send a shockwave outward that would ripple through the surrounding plasma, essentially using the sun itself as an instrument to measure the density of the material Voyager 1 was now sitting in. When that data came back, it lined up perfectly with what a region of interstellar plasma should look like, and NASA was able to announce with confidence that Voyager 1 had truly left the solar bubble behind. It is in the years following this crossing that the story of the Wall of Fire really takes shape. As Voyager 1's instruments continued gathering data from this newly entered region of space, something deeply strange showed up in the numbers. According to plasma wave data collected by the spacecraft, along with measurements taken from its still-functioning instruments, this transitional region just at and beyond the heliopause was recording temperatures far higher than anyone had expected, somewhere in the range of 30,000 to 50,000 degrees Kelvin. To put that in perspective, that is hotter than the visible surface of the sun itself, which sits at around 5,800 degrees Kelvin. It seemed almost impossible. Voyager 1 was leaving the warmth of the solar system behind, heading out into what should have been the cold emptiness of interstellar space. And instead, its instruments were recording temperatures that would vaporize almost anything on Earth in an instant. This is the discovery that eventually earned the nickname Wall of Fire, a phrase that captures the imagination immediately, conjuring images of some kind of blazing barrier standing between our solar system and the rest of the galaxy, as if the sun had built a final defensive perimeter of flame before releasing anything that dared to cross it. It is a dramatic image, and in a strange way it is not entirely wrong, but it is also deeply misleading if you take it literally, because what is actually happening out there has almost nothing to do with fire in the way we understand it here on Earth. To understand why a region of space can be tens of thousands of degrees hot without behaving anything like fire, you need to separate two ideas that we normally treat as the same thing: temperature and heat. On Earth, when something is hot, we usually assume it also carries enough energy in a small enough space to burn us, melt us, or set us alight, because the air and material around us is dense. A flame at a few thousand degrees can boil water in seconds and burn skin instantly because there are an enormous number of hot particles packed closely together, constantly transferring their energy into anything they touch. Temperature, in physics, is actually a measurement of the average speed and energy of individual particles, not a direct measurement of how much total energy is present. In the region Voyager 1 detected, the particles are moving unbelievably fast enough that if you calculated their individual energy, it corresponds to tens of thousands of degrees. But there are almost none of them. The density of particles out at the edge of the solar system is almost unimaginably low, often just a handful of particles in a space the size of a shipping container, compared to the trillions upon trillions of particles packed into that same volume of air here on Earth. Because there are so few particles to actually collide with the spacecraft, there is nowhere near enough total energy being transferred to Voyager 1's hull to cause any damage. The spacecraft can sail directly through a region that is, technically, tens of thousands of degrees, and not even register a change in its own physical temperature, because heat only transfers effectively when there is enough material present to carry it. It is the difference between standing in front of a raging bonfire and being struck by a single, blisteringly hot but incredibly tiny spark drifting through an otherwise empty room. One will burn you instantly. The other you might not even notice. So why does this happen at all? Why would the plasma at the edge of the solar system suddenly become so energetic in the first place? This is where the science becomes genuinely fascinating, and where researchers have spent years trying to build a complete picture. Near the heliopause, the solar wind, having traveled for billions of miles and slowed dramatically since crossing the termination shock, begins to pile up and compress as it runs into the resistance of the interstellar medium pushing back from the other side. This compression squeezes the charged particles in that region, and just like compressing a gas here on Earth increases its temperature, compressing this thin plasma at the edge of the solar system dramatically increases the energy of the particles trapped there. On top of that, scientists have found evidence of something called magnetic reconnection happening in this region, a process where twisted and tangled magnetic field lines from the solar wind snap, reconnect, and release enormous bursts of energy in the process, similar to the physics that powers solar flares back near the sun itself. Out at the heliopause, these magnetic field lines from the sun are colliding and interacting with the magnetic field of the interstellar medium, and every time they reconnect, they convert magnetic energy directly into heat and motion, accelerating particles to extraordinary speeds. The combination of compression and magnetic reconnection appears to create pockets of superheated plasma scattered unevenly through this boundary region, alongside patches that remain far colder, creating a kind of patchwork of extreme heat and near absolute zero cold sitting right next to each other in the emptiness of space, something that would be almost impossible to replicate or fully understand from any laboratory here on Earth. What makes this discovery even more remarkable is what it reveals about the shape and structure of the heliosphere itself, something scientists had long assumed was a fairly simple, rounded bubble, like a soap bubble, surrounding the solar system in every direction. But data gathered not just from Voyager, but from a separate NASA mission called IBEX, the Interstellar Boundary Explorer, which studies the edge of the solar system from an orbit near Earth, using a completely different technique involving neutral atoms bouncing back from the heliosphere's boundary, has suggested that the heliosphere is not a simple sphere at all. Instead, it appears to be shaped more like a windsock, or by some models, closer to a croissant, compressed on the side facing the direction the solar system is currently moving through the galaxy, and stretched out into a long tail on the opposite side, similar to how a comet's tail always points away from the sun. If that shape is accurate, it would mean the intensity of this wall of fire phenomenon is not uniform. Some sections of the heliopause boundary might experience even more extreme compression and heating than others, and the two Voyager probes, which crossed the boundary in slightly different locations and at different times, may have each sampled a different slice of a much larger, more complicated, and more violent structure than anyone originally expected. This brings us to Voyager 1's twin, Voyager 2, which took a different path out of the solar system and did not cross the heliopause until November of 2018, 6 years after its sibling, because Voyager 2 still had a working plasma science instrument. Unlike Voyager 1, whose equivalent instrument failed decades earlier, scientists finally had a second, more direct set of measurements to confirm what they had painstakingly reconstructed from Voyager 1's more limited data. Voyager 2 crossed the boundary at a different location and a different point in the sun's roughly 11-year activity cycle, and yet it recorded strikingly similar results. Plasma temperatures in that same staggering range of tens of thousands of degrees, along with its own surprises regarding the magnetic field structure in that region, findings that in some ways matched Voyager 1's data and in other ways deepened the mystery further. Having two independent spacecraft, launched decades ago with now partially aging or failed instruments, cross this boundary in different places and both come back with evidence pointing toward the same extreme, patchy, superheated structure, gave scientists far greater confidence that this was not some kind of instrument error or a one-off anomaly. It was a real physical feature of the outer solar system. One of the more surprising twists in this story involves the direction of the magnetic field itself. Before Voyager 1 crossed the heliopause, many scientists expected that once the spacecraft left the influence of the sun entirely, the magnetic field it measured would shift noticeably in direction, since the sun's magnetic field and the magnetic field of the surrounding interstellar medium are generally expected to point in different directions, shaped by entirely different sources billions of years and countless light years apart. Instead, when Voyager 1 crossed into what all other evidence confirmed was true interstellar space, the direction of the magnetic field barely changed at all. This was such an unexpected result that it briefly caused some scientists to question whether Voyager 1 had actually crossed the boundary, until the surrounding particle density data made it undeniable that the spacecraft truly was outside the heliosphere. The explanation that has gained the most support since then is that the sun's magnetic field lines and the interstellar magnetic field lines are not simply separate and distinct at this boundary, but are instead connected, twisted together, and reconnecting with each other in complex ways right at the heliopause, blurring what was once assumed to be a clean, sharp dividing line into something far messier and more intertwined. This tangled interaction between two entirely different magnetic environments, one born inside our solar system and one shaped by the wider galaxy, is very likely a major contributor to the extreme heating that creates the wall of fire effect in the first place, since magnetic reconnection release energy precisely in these kinds of chaotic, overlapping field structures. It is worth pausing here to appreciate just how remarkable it is that this information exists at all. The instruments currently measuring these extraordinary conditions were designed and built using technology from the 1970s, decades before anyone had a working theory of what the heliopause would even look like. let alone what temperatures might exist there. Voyager 1 and Voyager 2 are both powered by radioisotope thermoelectric generators, devices that convert the heat released by the natural radioactive decay of plutonium into electricity, since solar panels become completely useless at such enormous distances from the sun where sunlight is thousands of times fainter than it is on Earth. These generators lose about 4 watts of power every single year, a slow and unavoidable decline that has forced NASA engineers to make increasingly difficult decisions over the decades, shutting down one instrument after another to conserve the dwindling electricity for the instruments considered most scientifically valuable. Heaters have been turned off. Cameras were shut down decades ago once the spacecraft had left the region where there was anything left to photograph. Engineers have had to dig through technical manuals written by people who, in some cases, have since passed away in order to understand systems that have not been touched in 40 or 50 years, all in an effort to keep just enough instruments alive to keep collecting this extraordinary data from a region of space no other spacecraft has ever reached. Every additional year that these two aging machines continue to function and transmit information back across billions of miles is, in a very real sense, borrowed time. And scientists know that eventually, likely sometime in the next several years, the power will finally run too low to keep any instruments running at all, and Voyager 1 and Voyager 2 will fall permanently silent, continuing to drift onward through the galaxy forever, but no longer speaking to us. That inevitability is part of what makes this discovery, and discoveries like it, feel so urgent and so precious. This wall of fire phenomenon is not something scientists can simply go back and remeasure whenever they like. There is no other spacecraft anywhere close to that region of space, and there will not be another one for a very long time. Any future interstellar probe, even one built with far more advanced propulsion technology than the Voyagers had available in the 1970s, would still likely take decades just to reach the same distance, assuming such a mission is ever funded and launched at all. This means that for the foreseeable future, everything scientists learn about this superheated boundary between our solar system and the rest of the galaxy is coming from two aging spacecraft, running on fumes, using instruments that, in some cases, were never designed to survive this deep into their mission in the first place. Every new piece of data that trickles back is treated with enormous care because it may be one of the last opportunities in a generation to directly sample this environment. This also raises a fascinating and somewhat sobering question about what this wall of fire actually means for humanity's future in space. As dramatic as the phrase sounds, the reality that this region poses no threat to a physical spacecraft passing through it is actually reassuring in one sense, and slightly humbling in another. It tells us that the boundary of our solar system, while shaped by genuinely extreme physics involving magnetic reconnection, particle acceleration, and the collision of two entirely different plasma environments from opposite sides of interstellar space, is not some kind of barrier that would prevent future exploration. A spacecraft with sufficiently hardened instruments could, in principle, pass through this region just as Voyager 1 and Voyager 2 already have, without being destroyed. But it is also humbling because it reminds us just how little we still understand about the true structure of our own cosmic neighborhood. For most of human history, people assumed the solar system simply ended somewhere past the outer planets, with nothing much happening at the boundary at all. It took direct, in-person measurement from a machine that had already been traveling for over 3 decades by the time it made this discovery to reveal that the true edge of our solar system is an active, violent, dynamic frontier filled with compressed plasma, twisted magnetic fields, and pockets of extreme heat unlike anything found closer to home. There's also something almost poetic about the fact that this discovery was made by Voyager 1 specifically, the same spacecraft that carries the golden record. A phonograph disc containing greetings in dozens of languages, recordings of natural sounds from Earth, and a curated selection of music intended to represent human civilization to any intelligent life that might one day intercept it, drifting silently through the galaxy long after Earth itself may no longer exist in its current form. The same machine carrying humanity's message in a bottle to the stars is also the machine that first revealed to us just how strange and extreme the true edge of our own solar system actually is, a discovery made almost as an afterthought, decades after its original mission had already been completed many times over. Scientists continue to analyze the data streaming back from both Voyager spacecraft, piecing together a more complete picture of this superheated boundary year by year, discovery by discovery, working with a data set that grows more valuable with every passing year, specifically, because it can never really be replaced. Researchers have combined the direct measurements from both Voyagers with the wider, indirect mapping data from the IBEX mission, and more recently with data from a newer mission called IMAP, the Interstellar Mapping and Acceleration Probe, launched to build an even more detailed picture of the heliosphere's boundary from Earth's orbit without needing to travel there directly. Together, these different sources of information are gradually revealing a boundary region that behaves less like a single clean wall and more like a churning, uneven, and constantly shifting frontier, one that expands and contracts slightly as the sun's own activity rises and falls across its 11-year cycle, and one that likely looks completely different depending on which direction you approach it from, given the compressed, windsock-like shape the entire heliosphere appears to have as it plows through the surrounding galaxy. What ties all of this together? And what makes the phrase wall of fire such an unexpectedly fitting description once you understand the underlying science is the sheer contrast between what this region looks like on paper and what it would actually feel like if you could somehow stand there yourself. On paper, in terms of raw temperature, this is one of the most extreme thermal environments that any spacecraft built by human beings has ever directly measured. Hotter than the surface of the sun in places, hot enough that the very word fire feels almost like an understatement. And yet, if you could somehow survive the vacuum and radiation long enough to physically stand in that exact spot, wrapped in some kind of impossible protective suit, you likely would not feel any heat radiating against your skin at all, because there simply are not enough particles present to transfer that energy to you in any meaningful way. It is a region defined by blistering speed, rather than blistering density, a place where individual particles are flung around with more energy than almost anywhere else in the solar system, but where those particles are spread so incredibly thin across such an enormous volume of space that the overall experience would be closer to floating in an eerily calm, dark void than standing anywhere near an actual flame. This paradox, extreme heat without any actual burning danger, is part of what makes this such a compelling story, and part of why it continues to capture public attention years after the underlying data was first gathered. It forces us to reconsider assumptions we carry over from our everyday experience on Earth, where heat and danger are almost always linked together, and to recognize that the universe operates according to rules that do not always map neatly onto our intuitions. The edge of the solar system, it turns out, is neither the cold, quiet emptiness that science fiction sometimes imagines, nor a literal wall of destructive flame that would incinerate anything crossing it. It is something stranger than either of those ideas, a thin, turbulent, magnetically twisted region where two entirely different plasma environments collide across billions of miles of nearly empty space, generating pockets of extraordinary energy that exist almost entirely without consequence to anything passing through, precisely because there is so little material there to carry that energy anywhere at all. As both Voyager spacecraft continue their slow, silent journey outward, now traveling through true interstellar space, completely beyond the direct influence of our sun's solar wind, they carry on gathering whatever fragments of data their remaining instruments and dwindling power supply will allow, sending back information that took over 22 hours to reach Earth in Voyager 1's case, a reminder of just how vast the distance between us and this wall of fire boundary truly is. Every transmission that arrives is treated as precious, not because scientists expect some dramatic new revelation with every single signal, but because each one adds another small piece to a picture that has taken more than a decade to assemble, and that may never be fully completed before these two remarkable machines finally lose the power they need to keep speaking to us at all. It is also worth thinking about why a story like this spreads so quickly once it reaches the wider public, because the phrase wall of fire itself carries so much more weight than a raw number ever could on its own. If a headline simply said that a boundary layer far beyond Neptune contains plasma with an average particle energy corresponding to 30 to 50,000 degrees Kelvin, most people would understandably skim past it, because the description on its own does not immediately connect to anything familiar. But the moment that same discovery gets described as a wall of fire, something clicks. Suddenly there is an image, a boundary, a barrier standing between us and the rest of the galaxy, something almost mythological, like the edge of a map on an old sailing chart marked with warnings about sea monsters lying beyond the known world. It taps into something old in the way humans think about frontiers. The idea that at the edge of anything unknown, there might be a final obstacle guarding whatever lies beyond it. The fact that the real science underneath that phrase is even stranger than the myth, involving magnetic reconnection, particle compression, and a patchwork of scorching and freezing plasma sitting side by side in the vacuum of space, only makes the story more remarkable once people actually take the time to understand what is happening out there. This also says something important about how science actually progresses, especially when it comes to studying regions of space that are almost impossible to reach directly. Scientists did not simply theorize that this wall of fire might exist and then confirm it with a clean, single measurement. The picture came together slowly, over years, built from imperfect data collected by instruments that were never originally designed for this exact purpose, cross-checked against solar eruptions that happened to ripple outward at just the right time, compared against a separate spacecraft's magnetometer readings, and eventually reinforced when a second probe, launched at the same time, but taking a completely different path, arrived at the boundary years later and found strikingly similar conditions. This is often what real scientific discovery looks like, especially at the frontiers of space exploration. It rarely arrives as a single dramatic announcement. It accumulates piece by piece, correction by correction, until enough independent evidence points so consistently in the same direction that the scientific community can finally say with confidence that they understand what they are looking at, even if many of the finer details remain the subject of ongoing research and debate. There is also a broader lesson embedded in this story about the value of long-duration missions that nobody could have fully appreciated when they were first launched. When Voyager 1 lifted off in 1977, the engineers and scientists who built it were focused almost entirely on the flybys of Jupiter and Saturn, the images of swirling storms and icy moons that would dominate newspapers and magazines for years afterward. Almost nobody involved in that original mission could have predicted that the same spacecraft would still be operational and still making genuinely significant new discoveries more than 4.5 decades later at a distance so extreme that sunlight itself takes over 20 hours to reach it. The Wall of Fire discovery is, in many ways, a bonus chapter in a story that was supposed to have ended long ago, made possible only because engineers decades ago built in enough redundancy and made cautious enough decisions about power management that a handful of instruments are still limping along far past the point anyone originally expected them to still function. It is a powerful reminder that some of the most valuable scientific discoveries are not the ones we plan for in advance, but the ones that emerge slowly, unexpectedly from tools and missions that were built to answer completely different questions decades earlier. For now, the Wall of Fire stands as one of the most striking reminders of just how much remains to be discovered, even within our own cosmic backyard. It took spacecraft that have been flying for nearly half a century, built with technology that predates most of the computers, phones, and satellites that define modern life, to reveal that the true edge of our solar system is an active, energetic, and genuinely strange frontier filled with extreme temperatures, twisted magnetic fields, and physics that continues to challenge and refine our understanding of how our sun's influence finally gives way to the rest of the galaxy. And somewhere out there, drifting further away with every passing second, 2 aging machines are still listening, still measuring, still sending back whatever whispers of data they can manage from a region of space that human beings had only ever imagined until the moment these 2 small, persistent spacecraft actually arrived to measure it for themselves.